but it's my first time in São Paulo. But the talk today is basically right where I left 16 years ago, so that's where it starts. So I'm interested in positively curved manifolds and in torus actions on such manifolds. And it's joint work with Lee Kennett from Oklahoma and Michael Wiemeller, who is also in Münster. All right, so what's the basic problem in positive curvature? One of the problems is there are very few examples of such manifolds, right? So in the simply connected case, there are the crosses which have been there forever, so compact rank 1 symmetric spaces, SN, CPN, HPN, and the Cayley plane. And all other known examples are only in very few dimensions, so in dimensions 6, 12, 7, 12, 13, and 24. And only in the two odd dimensions there are infinitely many. So in all other examples, all other dimensions there are only one or two examples. Right. So that's one thing. And by comparison, there are relatively there's a relative rich class of examples for non-negative sectional curvature. So if you only have ask for non-negative sectional curvature, then you actually have quite a rich class of examples. So, for example, every compact homogeneous space inherits a metric of non-negative sectional curvature from the bi-invariant metric of the Lie group. So if you have a bi-invariant metric of a Lie group with a bi-invariant metric, it has non-negative sectional curvature, and any quotient has non-negative sectional curvature, and you get non-negative sectional curvature this way. And more generally, you can look at bi-quotients, so that's when the group doesn't just act from the left, but also from the right at the same time. As long as the action is free, you also get non-negative curvature on the quotient, right? So non-negative curvature is invariant under taking quotients by free isometric group actions, and that's why this is clear. And then there are, of course, it's invariant under taking products, and there are also some special gluing constructions which you can do, so this has been carried out by Shiga first, and then a rich class of examples was exhibited by Grove-Ziller, right? So that's one thing. So the examples are drastically different between non-negative sectional curvature and positive curvature. But on the other hand, that's the wrong way. As far as there's no explanation for this, none, right? So there's not a single obstruction known that distinguishes these two classes in the simply connected case, right? So fundamental group is quite different, but in the simply connected case, no single obstruction is known to distinguish these two classes. Two of the oldest conjectures in the field are related to exactly this problem, right? So the first soft conjecture says S2 cross S2 shouldn't admit a metric of positive sectional curvature. And then there's a second Hopf conjecture which says that positively curved manifolds should have positive Euler characteristic in even dimensions. Right? So these are two of the oldest conjecture, and we will address them under some additional assumption later on. And so the whole talk fits into the so-called symmetry program, which was proposed by Grove in '92. And he was motivated in part by a theorem of Xiang-Kleiner. So if you have a 4-manifold with positive sectional curvature and you assume in addition that the isometry group is infinite, so you have an S1 in the isometry group, then you actually can say it's homeomorphic to S4 or CP2, right? So it uses Friedmann's classification. And then by Friedmann's classification, you just need to compute, you need the right estimate for the Euler characteristic, right, since the manifold is simply connected. So in particular, it cannot be S2 cross S2, so that's in particular proves, of course, the first Hopf conjecture under the symmetry assumption. So if there's a S1 action, then the first Hopf conjecture is actually holds, right? This has been improved some years ago by Grove and myself. So you can actually do better than homeomorphic. You can actually do equivalently diffeomorphic, where the S4 and CP2 is actually endowed with a linear action. But that's not today's main topic. So, yeah, maybe I state the main results. So the main results are related to low-dimensional torus actions. So the first theorem says that if you have a 5 torus action on a positively curved manifold, and it's effective and isometric, then every fixed point component has a rational homotopy type of a rank 1 symmetric space, right? So, and okay, in odd dimensions, one has to. There's a small lie involved, because it could be that the fixed point component is not simply connected, but then you just pass to the universal cover, right? The fundamental group is finite, and rationally a sphere just means the universal cover is a sphere, right? So and the universal cover is yeah. Okay. So this implies the second Hopf conjecture, the one on the Euler characteristic, provided that you have symmetry rank 5, right? So if you have a positively curved even-dimensional manifold whose isometry group has rank 5, right? So then you can find a T5 inside the isometry group. And so it's even dimensional, then the fixed point set of this is going to be non-empty. That's Berger. So Berger tells you that every killing field has a zero somewhere. And so if you take a generic line here, which is sort of dense in the T5 and the killing field corresponding to it, this will have a zero, and then the 0 point has to be a fixed point of the torus action. So it is clear that this is non-empty, and of course the Euler characteristic of M to N is equal to the Euler characteristic of the fixed point set. Right. So, and every fixed point component is. Yeah, so the fixed point components are all even dimensional, I should also say, right? They cannot be odd dimensional, so the codimension is always going to be even. So if every fixed point component has a topology of a rank 1 symmetric space, then obviously the Euler characteristic is going to be positive, right? So we can characterize a fixed point set of fixed point components of low dimensional torus actions. Right, so I should say there were previous proofs of the Hopf conjecture under symmetry assumptions, but all previous results sort of depended upon a lower bound on the symmetry rank, which goes to infinity as the dimension goes to infinity, right? So either linearly, or if the dimension is divisible by 4, there was a paper by there's a paper by Ammann and Kennard where you only need logarithmic bounds, right? So dimension divisible by 4 logarithmic bounds were enough, but this is now, the first time that you only have a fixed number. 5 is enough, right? Okay. Yes, okay, so that's the second part. So that's the first main result, and maybe I should also mention the other main results. So the first main result was related to fixed point components. And then you can of course also ask, how about the ambient manifold, right? What can you say about the ambient manifold under some symmetry assumptions? And then you need to make additional assumptions if you want to say something. We cannot, at least for now, our methods don't allow sort of to say something without additional assumptions. So, but if the manifold is even dimensional, and you assume that the odd Betti numbers, so B odd means all odd Betti numbers of the manifold are 0. And you actually assume a slightly larger symmetry degree yet, right? So you assume now the rank of the isometry group is 9, not just 5. Then not just the fixed point components, but the manifold itself is rationally a rank 1 symmetric space, right? So that's a fairly strong statement, right? So there's of course here also there were previous theorems, right? So yeah, maybe I should mention one of the oldest theorems that started things by Grove and Searle. That actually also works with just S1 action, for example. So if you have an S1 action on a manifold, and the manifold has positive curvature, and the fixed point set has dimension n minus 2, which is the largest possible dimension it could have, right? So then it follows mn is homotopically equivalent to length space or CP n over 2. So yeah, it's actually not just homotopically equivalent, it's diffeomorphic. It's equivalently diffeomorphic, right? So you only need a S1 action there, but you assume something on the S1 action. It's a very, very strong assumption to assume that the fixed point set has dimension n minus 2, because what you can use then is that the manifold, so the key technique here is to use that the quotient space has boundary. And so once the quotient space has boundary, you can use the Soule theorem. So the Soule theorem, positive curvature, says that an open manifold with positive curvature is diffeomorphic to Rn, and here you can prove that the orbit space, which is actually an Alexandrov space, you can still prove it's contractible, right? And then once you get this going, you can actually prove this result, right? So yeah, so in a way it's only a S1 action, but of course there's a strong geometric assumption on the S1 action. The second theorem also makes an assumption on the torus actions. Now we actually assume even a larger torus, so 12-dimensional torus. That's probably not optimal. It should be 9. But okay. So we assume it acts isometrically on a manifold. It's simply connected again. We have positive curvature and we have a fixed point. And now we make an assumption that in the neighborhood of this fixed point, we don't have any finite isotopy groups, right? So it's a way sort of you assume something on the isotopy representation at a fixed point, right? So that's another way of looking at it. It's a different assumption than in Grove-Searle. It's weaker in a way, and the conclusion is also weaker, right? But it says then the manifold has a rational homotopy type of a rank 1 symmetric space. All right, so sure. No, only one. You need one component of dimension n minus 2, right? So you kind of have, in CPN, for example, you have the CPN minus 1 sort of fixed, and then you see there's one other fixed point, right? So that's basically what you prove. It corresponds sort of to the soul of the other orbit space. So there's only, once you know that there's one component of dimension n minus 2, you can actually see there's a unique point of maximal distance, a unique orbit of maximal distance to this component, and that's the only other point that could have non-trivial isotopy group, right? And then you can basically decompose the whole thing into 2 disk bundles and see the whole, classify the situation. Right. So, but the techniques are very, very different. So there's no real relation between the techniques here and there. Right. Yes. One thing I should say on the finite isotropy groups. What is this? Okay. I mean, this has some significance if you have a torus action. On a manifold, and so in even dimensions, it always has a fixed point. In odd dimensions, you can always find a codimension 1 subtorus with a fixed point, also by the Berger, by a theorem of Berger. So assume it has a fixed point with a fixed point. But now without any additional assumption, right? So then you can look at the, say, the epsilon neighborhood of P, right? Which is, of course, right. So the torus acts, of course, on the epsilon neighborhood of P, and that's, of course, equivalently diffeomorphic to the action on the tangent space. And now you can look at so in general, of course, this representation will have points with finite isotropy groups, right? So you can choose a vector, choose Q in the epsilon ball with maximal finite isotropy group. So I should say, of course, so the principal isotropy group, if the action is effective, is always trivial, right? So the trivial group is always occurs as isotropy groups, but in general, finite isotropy groups do cause problems. That's sort of the moral of today's talk. So maximal finite isotropy group, and now look at the fixed point set of F. So the fixed point component containing this fixed point, right? And now here, of course, you will have an action of a torus. And now in the neighborhood of this fixed point, there will be no finite isotropy group anymore, right? So you will always see totally geodesic submanifolds, even in general, such that the assumption C is satisfied, of theorem C is satisfied, right? So in general, you can always arrange for a torus action. So there will be these totally geodesic submanifolds, so that the assumptions of theorem C are satisfied, right? And then these guys have to be rank 1 symmetric spaces, at least rationally, right? So so that's. Yeah, it's not clear whether you can. That's one of the open problems. How much you can do more with other coefficients. So with integer coefficients, right? So, but one thing one can say here is if it's an even dimensional sphere, so Sn with n even, then it's actually homeomorphic to an even dimensional sphere. Also with the same with the first theorem. So if the fixed point component of a 5 torus action is an even dimensional sphere, then actually it's homeomorphic to an even dimensional sphere, not just rationally equivalent. Okay. Yes, so I should pay attention to time. Okay, I'm okay. Right. Okay, so tools from previous work. So one of the main tools is this, which sort of combines several results in the literature. It wasn't quite stated this way so far, but That's how one can put it. So if we have a positively curved manifold, and we have two totally geodesic submanifolds that intersect transversally, and the codimensions add up to something which is still less than n over 2, then the rational cohomology of the manifold is actually 4-periodic, so which is very strong, right? So yes, rationally 4-periodic, that means there exists a class E in H4 such that cupping with this class from E, from H0 to, so in the first degree it only has to be surjective to H4. Surjective, right, which is basically just saying the Betti number is at most 1, right, or this class is 0, right? Okay, and then in all other degrees where it possibly could be, it's an isomorphism. It's an isomorphism for I runs from 1 to n minus 5. Right, so that's what periodic cohomology ring means. That's what periodic cohomology ring means, right? So, and once you have it 4-periodic, you are not so far from rank 1 symmetric spaces, right? So it turns out you are actually pretty close already. Yes, so let me maybe explain how this comes about, this result. Yeah, should I? Yeah, okay. So there's one theorem is a connectedness lemma. So, yeah, let me just put the second version on. So it says that the intersection into N2. So we assume that K1 is smaller or equal than K2. So then there's a lemma that says that this in general, so even if the intersection is not transversal, the inclusion map is N minus K1 minus K2 connected. So that's actually one of the results I talked about in Brazil 16 years ago. Right, so this means that you get an isomorphism on cohomology. So the inclusion induces an isomorphism on cohomology in all degrees where you could possibly hope for, right? And in the last degree, it's only injective in cohomology. Okay, right, so and once you have this, and you assume in addition that this intersection is transversal, so that this is the dimension of your manifold, then you actually know that you get a period in your cohomology ring, but not just with rational coefficients, but with integral coefficients, right? So this implies that N2, so the cohomology of N2 with Z coefficients is K1 periodic. And this is pretty simple. You have a Poincare duality here of the submanifold, and you have a Poincare duality of your ambient manifold. And then you just compose those two Poincare dualities, which are always isomorphism, and compose it with the inclusion or the map on cohomology induced by the inclusion, and the map on homology induced by the inclusion, and you get your period, right? And this will be, the period will actually be the Poincare dual of the fundamental class of the submanifold. The guy giving you the period. Okay, so, and then there's a 4-periodicity theorem, so that's one lemma, and then there's a theorem by Lee Kennard from 13, from a speech D series. So if you have a manifold, or just a space, doesn't really matter, and H star of X has, with Z coefficients, has K1 periodic. Is K1 periodic? Let me give it a dimension. So up to dimension n. So right. So yeah, and 3 times K1 is less than n. Then this implies that rationally you are actually 4-periodic. So you get right away back to 4-periodicity. So this theorem is a really clever application of cohomology operations. So Steenrod squares and the analog in these 3 coefficients. It's sort of similar to Adams' classification of spaces which are generated, whose cohomology ring is generated by just one element, so the main observation is, and you have to work for it, that lots of things can be carried out if you only have a period in your cohomology ring, rather than the assumption that the whole cohomology ring is generated by one element. So then you get this 4-periodicity. Okay, so that's one assumption, and then yes. So if we want to prove this the theorem on the fixed point set, then of course we can also use this trick I used before. So we have a T5 action on our manifold. We have always positive curvature, and we have a fixed point P in MT5. And then of course we can use this trick from before, sort of take an isotropy group, a maximal finite isotropy group in a neighborhood of P, and pass to the fixed point set, right? So F maximal finite isotropy group, and then of Q in the neighborhood of P, and then replace Mn by Mn fixed point set of F with the fixed point component FF at P, right? And of course now the torus will still act. So the quotient torus will still act, and we still have a effective representation of a torus, and the fixed point set of course hasn't changed. And what we have gained now is the representation, so T5 acting on TP Mn 0F, T5 modulo F has no finite isotropy. And so the second, to some degree, the main point, or one of the main points, is that this is something really, really special. So to have something, a representation of a torus without finite isotropy, that's those representations have lots of rigidity properties, right? So if you have a representation of a torus, you can just identify it with an element of H2 of the classifying space. I mean, there are different ways of doing it. If I have time, this will come up again. That's why I put it this way. So by taking the Euler class of the bundle, of the corresponding bundle over the classifying space, And now, if you have a representation, of course it decomposes into two-dimensional representations, and you take a maximal collection now of pairwise inequivalent sub-representations, and we denote by W1 to WH the corresponding element in H2. And then that's a fairly simple lemma here. So there are no non-trivial finite isotropy groups for the induced action on the space, if and only if these elements have the following properties. If you have D linear independent vectors, they form a Z basis. So that's what you have to deal with, right? So for any such representation, you can associate a finite subset E of Z to the D with the property that E cap minus E is the empty set. That sort of corresponds to the fact that the representations are inequivalent as real representations. So if W and minus W correspond to equivalent real representations. So that's why you have this. And span Z of E is equal to Z to the D. And every D linear independent vectors in E form a Z basis, right? And yeah, and a lot of the work actually of the proof of the theorem is actually to analyze this combinatorial property, right? And the surprising thing is you can say a lot, right? So there are lots of structural results. It's a mystery to me why exactly that is, if it is related to something, but right. So you can prove quite a bit on these finite subsets, right? So for example, you can find a subgroup of co-rank 1 such that E without this without the elements in the co-rank 1 subgroup are actually linear independent, right? So that's actually a very strong statement, right? So, for example, it does give you, in particular, the optimal bound on E, right? So, a priori, of course, there's no upper bound for the set E, but it follows automatically that the order of this set is at most D times D plus 1 over 2, right? And you can do an equality discussion, right? So the moral of the story is, so if you have such a representation, then, so of course the dimension could still be very big compared to the torus, right? But actually, then there must be lots of equivalent subrepresentations, right? So you actually see lots of equivalent subrepresentations. So that's one of the corollaries. Okay. Yes, so for us more important is the following lemma, right? So we just take any representations, we don't assume anything on it, except that it is faithful. So we have a faithful representation on the torus. There can be finite isotropy, doesn't matter. Then the conclusion is so the dimension of the torus is odd. There's a D-dimensional subgroup. Yes, so H such that the induced representation on the fixed point set is faithful and of product type, right? So what's our aim here? Yeah, let me try to explain it for T7. Okay, so we suppose we have a 7 torus acting on our manifold now with a fixed point. And of course the action is always assumed to be effective, P. And we apply this lemma, right? So there exists H. H is not necessarily connected, right? So, but the dimension of H is So so that we can look at the fixed point set. The component containing P. Yeah, let's call this F. And now F4 torus, which is given by the quotient torus, still acts effectively on TPF. And so this representation is basically a product representation, what we call a product representation, right? So we have here, this is S1 cross S1 cross S1 4 times. And the representation is effective, but only consists of 4 non-trivial inequivalent subrepresentations, right? So so basically the subrepresentations, there's a product decomposition in such a way that the subrepresentations are given by the projections to the 4 factors, right? And that in turn means that the fixed point set of S1I, right? So that's sort of S1I is 1 cross S1 cross 1. So it's an I stage and fixed point set of S1J intersect transversely. In F, right? So you can always arrange, you can always find a totally geodesic submanifold such that inside this totally geodesic submanifold you do find totally geodesic submanifolds that intersect transversally, right? And that's what you need to get to make use of this this statement, right? So we want to bring ourselves into a situation where we find inside a totally geodesic submanifold, we actually have this situation. We find 2 other smaller submanifolds of the submanifold which are totally geodesic, intersect transversely, and such that the intersection has still half of the dimension, right? And this we can do now here if you have a 7 torus. So basically each of these S1s has a certain codimension, and we actually take the 2 S1s with the smallest codimension, right? So fix a codimension of Fi. Si is Ki, right? And then of course K1 plus K2 plus K3 plus K4 is equal to the dimension of F minus the dimension of the fixed point set. Right, so and in particular the codimensions, the smallest 2 numbers here still have a codimension K1 plus, so if we assume K1 less or equals than K2 less or equals than K4, then we have K1 plus K2 is less or equal than F over 2, right? So if F is the dimension of our submanifold, right? So we can actually apply this result. Okay. Yes. Right. So yes. So there. Once you have 4 periodic, you're still not quite done. You still need to work a bit after that, right? So, and the main tool there is equivalent cohomology, right? So, right, so if we have a torus action on a manifold, then one looks at the cohomology H star TD. cross whatever coefficients, that's given by the H star of the Borel construction. So you cross it with a classifying space and divide out the torus. And right, so using calculations in equivalent cohomology, you can relate the fixed point set of the manifold to the fixed point set to the equivalent cohomology of M, right? So so for example, one result. So if the spectral sequence, so this is a fibration. M cross TD, there's a fibration, ETD to the classifying space. And using our connectedness lemma, we can sort of often show that the spectral sequence of this fibration degenerates, right? Which means basically that the rational Betti numbers of the total space are the same as the rational Betti numbers of the product of these two guys. So at least as the homology looks the same as the homology of a product, right? The ring structure might still be very different. So often one can relate the cohomology to the one can often bring oneself into a situation where one has a torus action for which the spectral sequence degenerates, and then one has a property that the equivalent cohomology ring of the manifold injects into the equivalent cohomology of the fixed point set. And of course, the equivalent cohomology of the fixed point set is just a product, right? I mean, Z. But here you have more components, right? And using these sort of tricks, one can show that for periodic cohomology ring, the few examples that are there, which are not crosses, actually cannot show up, right? So let me talk about what's the enemy. Right, so the biggest enemy which sort of doesn't fit at all into the picture is in dimension 4n plus 4k plus 2. And you could have a cohomology ring like that, right? So H star of Mn with rational coefficients. So you could have that the first Betti number is equal to the second Betti number is equal to 0. The third Betti number could be arbitrary to G, and the fourth Betti number, no, that's bullshit. The first Betti number. The second, the second Betti number is 1. The second Betti number is 1, and that's equal to the fourth Betti number. The first is, of course, always 0 because of there's only finite fundamental group, right? So you always get 1, 0 for free. But yeah, so this is consistent with and then you have it 4 periodic, and 4 periodic, right? So such a cohomology ring makes sense, right? And by general theory, such manifolds do exist, right? So which have this sort of cohomology ring. And so the way you rule it out is, so you have as one action on such a manifold, such that the fixed point set, the inclusion map of the fixed point set, one fixed point component is 7 connected. So in positive curvature, you could immediately bring yourself into that situation, because otherwise we could never conclude that the thing has 4 periodic homology. And then you show, well, if G is not equal to 0, implies there are other components which are not simply connected, which have infinite with infinite pi 1, with B1 Fi positive. And that's your contradiction, right? Because the other components are also even dimensional, and then you actually get your contradiction, right? So right, using sort of this equivalent homology, you can use this, right? So that rules out that's the first enemy where this G is equal to 0, right? And then otherwise, the only other enemies left are S2 cross HBK, and S3 cross HBK. So once you have ruled out this examples, and you know already it's 4 periodic, you are left with these two guys. And there you basically do something similar, again arguing with equivalent homology, right? So you assume you have a torus action such that the spectral sequence degenerates, and in this case you show that there must be other components which are of the form S2 cross CPK something. And this is already ruled out before, right? So it could be that at one fixed point the fixed point component looks like S2 cross HBK, but you can then show there must be other components where the fixed point set looks like that. And that's already ruled out by basically because this guy doesn't have 4 periodic homology, right? So this is not one of the allowed pictures. Okay. All right. Yes. What's that? Oh. Right. Yes. So So the last few minutes, maybe I talk about the second theorem, theorem B. Right. Let me put it back on. So how do we get the ambient manifold under control under these assumptions? So if the odd Betti numbers are 0, right? So we have a T9 action on our manifold, so it's even dimensional. And so then the spectral sequence, so we look at the equivalent homology. And of course, if there are only even Betti numbers, then the spectral sequence will degenerate, right? So the bet has the same Betti numbers as M2N cross BT9. Okay, and right. So then there's work by Chang and Scale Brett, right? Which helps to understand how this map. So from the equivalent homology, so you want to compute what the image of the equivalent homology with rational coefficient into the equivalent homology of the fixed point set. So this map is injective, right? So that's an important thing, right? and we want to compute its image, right? And the image you can compute with one skeleton. So we define the one skeleton as the set of all points in the manifold such that the dimension of the orbit is at most 1. So the isotropy group is 8-dimensional, or it's a fixed point, right? And so then one of the results says that the image, iota star, image of iota star is equal to image of H star T9 M to N with rational coefficients, and then you look at H star into the fixed point set again. T9, T7. So that is the fixed point set always. So you look at the equivalent cohomology of the manifold, you look at the equivalent cohomology of the fixed point set, that's of course just a product. And this goes into this, right? So the map on cohomology is this way. And this map is going to be injective, right? So this is fairly elementary to see. And, right. But this has the same image as the image from the one skeleton. All right. And so the basic setup is now that, of course, we have a lot of space, right? So we have a 9 torus. So we do know that the fixed point set of every 5 torus already is a rank 1 symmetric space, right? So the 1 skeleton lies inside the 2 skeleton. In the 3 skeleton, you can define all that, right? And all this is already a rank 1 symmetric space, at least rationally, right? So, and the basic idea is then compute the image of, say, iota star du. By constructing a linear model. For the action. So, and by linear model I mean an action on an actual rank 1 symmetric space, which basically has the same structure. So you see the same sort of fixed point components, at least on the one skeleton, everything looks the same, except, and that you can afford since you work with rational coefficients, maybe components of isotropy groups, right? So there could be, the two actions could have sort of, have the same identity component, but maybe there are additional components for the one action and which are not there for the other action. Right, and so why this works is you need a pretty good understanding of actions on, need to understand actions of tori on rational CPNs and HPNs. Of course, also on a sphere, but on a sphere it's pretty easy, right? So, should I? No, time is already up. So, you basically know that for every, so actually we two of two of the dimensions of the torus we throw away by basically assuming we have a 7 torus action which has a 4-dimensional fixed point set. And then we know for the 2 skeleton of this fixed point set, we still have everything under control, and then we sort of can control this, the one skeleton, the image of the one skeleton by sort of creating this linear model, right? Yes, and for that one needs to understand, abstractly tori of actions of tori on these spaces, and this was done by Xiang and Xu. So this actually has been done, right? So and we can basically use their work sort of to figure out what's going on. Okay, thanks.
It's time for questions now. Yes, of course.
So, where did positive curvature enter?
Right. Yes. That's a good question. So, of course, in this connectedness lemma, right? So, yeah, and sometimes, of course, also, yeah. So fixed point components have, if they have dimension larger than 1, then the first Betti number is 0. That sometimes plays a role. But so the main thing is, yeah, I only mentioned one version of the fixed point component, a fixed point of the connectedness lemma. So this is totally geodesic and closed. Closed. So then the inclusion map of this into a manifold, so if we have this situation, is n minus 2k plus 1 connected. That's what the first part of the connectedness lemma, and then there's one with 2 components, which is slightly more complicated, but actually for our purposes somewhat more important. But let me explain this, right? So the proofs are pretty similar for both cases. So you look at the space of all curves that starts and end in n, right? So all gamma with gamma of 0, gamma of 1 is in n. And you do more theory on the space, right? So you have the energy function, and of course, n itself sits inside this space as a space of point loops. So n itself corresponds to the constant loops, and now the critical points of the energy functions are geodesics, n minus k are geodesics that start and end perpendicular to n, right? So that's a critical point, and every critical point C of positive energy satisfies that it is such a geodesic, right? And then you can show that the index of this critical point is larger than n minus 2k plus 1. And the way you show it is you compute the parallel vector fields that start and end tangentially to n, right? So, and that's by purely linear algebra, that dimension is at least n minus 2k plus 1. And whenever you have a parallel vector field along a geodesic, if you vary along this vector field, the length gets shorter, right? And since this is totally geodesic, the parallel curves will still be in this path space, right? So, so if you exponentiate a parallel vector field, you will still have a curve inside space, and the length gets decreased. That's how you get this index estimate, and that means that the inclusion map of n minus k inside this loop space, or this path space, is n minus 2k connected. Because all the critical points afterwards have index n minus 2k plus 1, and that happens to be equivalent to this statement. So that's how you, and that's the main point, actually. Yeah.
Further questions? How did the arithmetic of the dimension of the torus enter?
Yes. Yeah. So we have. Yeah, I kind of explained the proof of the fixed point set for a 7 torus, right? So, and you just need to push it a bit so that you can push it to a 5 torus, right? So, I mean, once you deal with representations of tori without finite isotropy groups, you deal with a finite set, right? So each one has only finitely many possibilities, except for multiplicities of the representations, which don't matter too much. And then it's just to some degree it's more a coincidence. There's no right. So you need to work more for the 5 torus, but I don't think for 4 torus that's not good enough. So the methods don't really work. It's not good enough to get a contradiction to this connectedness lemma, right? So it's not really right. I guess there probably are examples where. Actually, I haven't checked whether probably the examples at least should be good enough to show that you at least need a 3 torus or something, right? So I mean there are some 24-dimensional manifold. I'm not sure what the fixed point set of 2 torus looks like if they are all rank 1 symmetric spaces, or if the 6-dimensional guy. Yeah. Probably the 6-dimensional guy is a totally geodesic submanifold, and it's a fixed point set of a 2 torus inside the 24-dimensional guy. I think that's what it is. So a 2 torus is not enough, right? 5 torus does it, right? Everything in between is an open problem for your session.
Okay, thank you. If not, let's thank Burkhard again.